Very good. Just to remind you what we did way back in the Euler's equation, we discussed this differential operator on quantity theta. At that time, that theta was pressure, P. And we asked how would that change relative to a differential element where you move by a distance of dx. We said, well, it's theta plus d theta. And this d theta is represented by rate of change of theta with respect to x times the distance you move, dx. Do you remember that? Do you remember that? We did the homework on that, on the Euler's equation in the normal direction. We went through that detailed derivation. So this should not be foreign to you. And we are coming back to that now, except we're going to do it in a much more sophisticated way for both continuity and then momentum. So that's, as a backdrop, what I like to do. Let me do this diagram here so that all can see. I'm going to ask myself and put that theta as low u. Anyone want to make an interpretation physically what's low u represent in terms of mass flow? What is that? M naught divided by what? An area. Very good. So I'm going to have quantity theta represented by rho u. And what's coming out on the right side is theta plus d theta with respect to x of the quantity theta times the distance I move, dx. So that's just what I erased it. Except theta now become rho u. Do you get it? Any questions so far? So from that, my next step is from the diagram above, quantify the inlet mass flow rate to my control volume. So the m dot on the left-hand side. So I want to express that in terms of the diagram above. So it's simply rho u times an area. What's that area? Anyone? Area perpendicular to my velocity, rho u. What area would that be? dy times what? dy is times 1. Right? Any question on that? The term on the right, leaving my control volume, then become theta, copying what I have above on the top diagram, and multiply by the same area perpendicular to my velocity, which is dy times 1. Any question on that step? Any question on that step? Okay, so now I can create a table where I call the phase XYZ and I have two other columns, outlet and inlet mass flow, as dictated by that diagram. In 2D, I have only two surfaces, and we just done with the U surface. So I'm copying down what I did on the board in the center over on here. Can you follow? Let me stop. Can you follow? So a 3-column with 2D, only two surfaces. The first one is what I have done in detail. Any question before I continue? Now, can you infer what that mass flow will be on the Y surface? Do you understand the question? So I've done the horizontal mass flow, left side and right side. I'm now asking you to do the one perpendicular, top and bottom to the board. What will U be replaced by? V? Very good. What about the area perpendicular to V? dx times 1. Can you see it? Do I have to go through that? If you don't, this is something you should do at home to rederive the equation. So you understand how it comes about. So I now have the corresponding equation for 2D problem. Do you understand it? Questions? No? Everyone is on board? Okay, so now I want to extend that to 3D. Instead of 1, if I have in 3 dimensions, what will I replace the unit depth by when I have a 3rd dimension in the Z direction? Instead of 1, what will I replace that by? 1 is dimension into the board on here, the Z direction. If it's no longer 2D problem, I have to replace the unity depth by what? Anyone? D? Z. That's the dimension that I'm adding. That I deducted before. Right? Questions? Questions? So can you now, by inspection, fill in the missing blank of the 3rd equation in the Z direction? I mean, if you need to, you can go through the same exercise I did in the X direction. It'll just be repetitive. And I think you're smart enough to be able to infer that based on the other 2 directions in X and Y. So instead of V or U, what should that velocity be? W. Any question on that? Okay, now the area. What is the area perpendicular to W? Yes? Very good. dx dy. Thank you. And likewise, on the right side, dx dy. And the change is with respect to z, so this now completed my 3-dimensional analysis of mass flow in versus mass flow out. That sounds familiar to what we start with for the control volume shown here. This is mass flow out minus mass flow in. And I did it. The difference is I did it in the differential volume. So I can now take my final step, which is for the term that is shown here for the global average integral control volume approach. I'm going to have to represent this term by now my differential element, which consists of a differential volume which I can approximate to dx, dy, dz. So now I'm succeeded in having every term I needed from the global control volume formulation. And steady term now represented by this. Mass flow out minus mass flow in is shown by these two columns. So I'm going to put it all together into one big gigantic equation, whereby this now represents my unsteady term, equivalent to the control volume formulation. Column A minus column B is the difference of my mass flow in, my mass flow out minus mass flow in. And some of the term just drop out or cancel it when we do that. So the terms that get canceled out, and I can show it here, are those terms. Do you see that? And it's typical of a differential element analysis. You have the theta term, which I erase. The theta term on the right, so you have theta here, theta plus d theta with respect to x. That d theta term, when you sum the difference, always just cancel. You see it in Euler's, and you see it again now. Yes?
I'm not really seeing how it cancels or...
Okay. It's a little bit... When I go to 3D, let me make sure I have everything correct. So the way it cancels is, let me show one example. So this term, which is on the in-net mass flow being negative, is the same as, let me write it out so that you can follow. This term, if I break it up, we'll have rho u dy dz. Rho u dy dz, which is exactly the same as this one. So that drop out. That's what I meant by cancel. And what left? What left is now my term here. So I'm taking my outlet mass flow rate as dictated by control volume continuity. out minus in. And when I do that, I'm doing nothing but take column A and subtract of column B. And the first term, that's the theta term, appear on both sides, and it just disappears. Yes, any questions? Okay? As in most differential analysis, at the last step, all the independent variables of dx, dy, dz can be factored out. It's not intuitive, but when you think about it, it makes sense, because that cube, when we go through the derivation, always consists of dx, dy, dz, and it's a common term for everything, and it can be factored out so that when I'm done, I have now the equation I presented to you at the beginning of the lecture today, which we use for some special cases and example, and that's the same equation I have on here. So we did it. We did it painfully, but systematically. So let me pause and prepare myself for any questions, because the next question is for me to ask you. What are the assumptions? You get to this point. Okay, first, any question as to what we have done? That's the foundation, because in a moment, in the next 10 minutes of the lecture, we're going to take this same approach, apply that to the equation of motion for momentum, much more involved. This is the simplest, this is the very basic, this is the building block, but the approach is the same. Do you have any question on that? Everyone's good? All right. Okay, now tell me what are the assumptions involved, if any. And the last one is tricky. So let me start with the two easy ones first. Is this equation only for steady problem, or it's good for both steady and unsteady? Both. Very good. Very good. Why? Because I have accounted for the unsteady term at the outset. I didn't say it was steady. At the mean of accounting for any time change in my problem, so it's applicable for both. Viscous or inviscid. In my derivation, did I say anything about viscosity? Did I say, well, here's friction, here's how I'm going to tackle it? Yeah? What is the answer to that? It's both. It's both. It's a general equation that can be applied to unsteady and viscous flow. Now the last one is tricky, so don't answer it yet. I'm going to pose the question, and I want to remind you of what we did in Euler's streamline, because that was like a month and a half ago. Did I assume constant density? Did I assume constant density? Back in the streamline Euler equation, you went through the same question. Okay? The equation of Euler as derived, I asked you, if we had to assume the density is a constant in this differential element, what was the answer then? Do you remember? I bet you many of you don't.
It was incompressible.
What?
I guess that was incompressible.
No. The argument then was, because I'm defining a differential element, I can continue to string this and make it as small as possible to where it's just one point in space. And that is the density unique to that point. And in so doing, I don't have to assume anything about the density. It can be variable, meaning compressible, or it can be a constant. The same argument holds in here. In all the derivation, by definition, my differential element can be infinitesimally small, a point in space, of which the density within that point is not necessarily assumed to be constant. And hence this general equation will allow us to deal with changing density flow. And that is accounted for with the derivative of density inside those brackets for both steady or otherwise unsteady continuity. So the answer to that trick question is, this equation is good for everything, anything. Unsteady, viscous, changing density flow. So this, in a way, is presented, is good for any fluid problem. Right? Do you understand that? Yes.
How would we account for friction if there was in this equation?
I'm sorry?
If there was friction, how would we account for that using this equation?
Continuity had nothing to do with friction when you think about that, right? This is something I try to emphasize in the pipe flow. Remember in the pipe flow I said, continuity is continuity. Nothing to do with this. Forget about differential element. Remember in the pipe flow I said, if I have OVA coming in on one end, I must have OVA coming in on the other end. Friction or no friction. Now, if there's so much friction that the flow doesn't make its way through to the other side, all right, because it's so viscous, then when you start the flow on one inlet, the flow that will come out on the right side, that becomes unsteady flow. Okay? So continuity is different than, it's not OVA in and OVA out. That is how friction can come into play for continuity. Otherwise, if it's a steady problem, I don't care how viscous the flow is, what comes in must equal to what goes out. So the pressure that you ask, and the shear and the viscous effect had no bearing on continuity whatsoever. That must be reminded. Okay? The only exception is when the flow is so viscous, what comes in doesn't equal to what goes out. That's not a steady problem. Does that make sense? Okay. Questions? So now what I want to do is build on this. And ask ourselves what we will see if I use the same analysis and try to come up with the Euler's equation of momentum. So this is where we will not have the time to do a deep dive. And what I can only show you is the approach of how I end up with this equation of Euler in x, y, z coordinates. This is the end result. All right, and the derivation is presented in your text, so you can read it also at your leisure. But before that, let me remind you of what the Euler's equation looked like in the streamline coordinate as a comparison. So at least you can draw a parallel between these two sets of equations. This is in your handout that was posted yesterday, so you can pull it up and look at it. So back a month and a half ago, we have a cousin of the equation that is on this screen now, in that we deal with a 2D problem where we have some assumption involved, quite a few. Anyone remember what they are? Of this Euler's equation? Low gravity. Just to keep the algebra simple. What else do I assume? Inviscid, yeah, by definition, Euler is inviscid and steady. So we have this equation. And now, by inferring and extending what we did for the continuity equation, I have now an equation in the x direction that look kind of similar to the Euler's equation in the streamline coordinate. I have a dp ds versus a dp dx term. On the right, I have a convective acceleration, which is shown on here. And what has been generalized now is I can account for gravity, I can account for unsteadiness. Okay? So if I were mean, and I ask you for Thanksgiving break, since you have nothing to do, I want you to derive this equation. How would you do it? Anyone want to tell me how you would start?
Continuity.
Well, continuity is done. We are moving on beyond continuity now. I'm just asking for an approach. How will you even approach this problem, let alone doing it? Differential element. You start exactly like we did with continuity, which, as a reminder, I know we just did it. So let me do it here. For continuity, we just did it by saying I have a dx, a dy, and I have theta, which we call rho u a divided by a. That's my theta. That's my mass flux for my approach to derive the continuity equation, right? Now, if I were to come up with a momentum equation, what I have to do is to have the same approach, dx, dy. The theta now become my momentum flux, which is rho 3a, that's my mass flow, times the velocity u again. And that's per unit area is now my new theta for the Euler's equation, which is the equation of momentum. So instead of mass flow, now you have momentum flow. You do the same on the right-hand side of theta plus d theta, and you continue just like we did on continuity. You do it in 2D, and then you extend it to 3D. Can you do that? You see how all this is heading, right? If you do that, you will be successful in proving the term on the right. And the remaining term is the driving force of body force and gravity, gravity of body force and the pressure gradient. And that comes about just like we have done with the Euler's equation back in here. So you are capable with all the background that we have covered of deriving these three equations, one in each direction, potentially. All right? Yes?
So the contribution from GX, GY, and GZ, is that assuming that our coordinate system isn't like necessarily the conventional way we think of it?
Exactly. So I have now x, y, z. The g vector can be in any orientation that gives us component in I, j, k direction. It doesn't have to be oriented specifically parallel to y. It can be general. But in most engineering applications, you have a preferred direction like we will see for the inclined plane homework problem that's after Thanksgiving. So I want to pause to make sure you have a feel for how this comes about. Anyone? Any question? Now, here's a punchline, and I have 2 minutes for that. This operator is just like we showed you early in the beginning of the lecture, is a gradient. So this is now a pressure gradient. It's just algebra that you're capable of handling yourself. The G can be represented by a vector. So at the end of the day, by using a total acceleration, which is all that in the bracket on the right, like I started the lecture today, which is behind the screen. I have acceleration on the right, density, just like here, density, acceleration, and a pressure type gradient term on the left. Can someone read me, which we did in the Euler's equation back a month ago? Can someone read me, what is this equation resemble F equal to ma, whereby here is my acceleration, here is my mass, divided by what? A volume. That's my right-hand side. What's my left-hand side? What's pressure divided by a length? What's pressure divided by a length? What is pressure? Force divided by an area, and then divided by length again, force per. Isn't that nice? After all this hard work, all this sweat, and all this algebra, it's nothing but F equal to ma. It's the same old equation that you always use, which is what we did, how we start this derivation, remember? So it comes in a full circle. It's coming in a full circle, except now it's much more sophisticated because of fluid. It's deformable, we have convective acceleration, blah, blah, blah. But at the end of the day, it's still F equal to ma. So next time when we come back, we're going to flow in viscosity, and it's going to be very dicey.